So let me introduce the first talk by Dr. Yu. He is a professor in National University of Singapore, and he gave a talk about a robotic platform integrated with FES for gait rehabilitation. So Dr. Yu, it's your stage.
So we can start. Yeah. Okay. Good morning. Good evening. Wherever you are. I hope everything is going on well with you in this pandemic situation. So today I'm going to introduce very quickly about some of the testing results of one of our projects for gait rehabilitation. So if we look at how conventional gait training are being done for neurological disorder patients like stroke or spinal cord injury, it's very, very labor intensive. So you see that therapists need to assist the leg movement, and another therapist need to assist the trunk movement and plus bodyweight support. So of course, for less severe patients like this, they can walk over ground, but still need another therapist to assist, mostly labor intensive also. So how do we reduce the requirements of human labor? This therapist now is in a very big shortage everywhere. So, and also of course, how do we increase the intensity of training? And other questions we might ask is, should we do gait training on a treadmill or overground? Or how do we look at the conventional therapy if we want to use robots? Is the pelvic motion restriction a problem? So these are the questions we would like to take a look. So of course, these are robotics device fixed on a treadmill with bodyweight support and leg movement assistance. So these are commercialized and they have demonstrated the effectiveness. But of course, they are all very expensive and constrained onto a fixed platform. So if we look at the difference between walking on a treadmill and overground, even for healthy subjects or healthy people, study has indicated the difference after training. So if you walk on a treadmill for long and you walk on the ground, you feel the difference. So basically, the gait parameters will slightly be slightly different. And also the movement of the range of motion and pelvic rotation and all this will be different. So if you really want to train the patient to achieve more natural gait, walking over ground might be a better option. Another question we want to ask is that we know that in normal healthy gait walking, the role of pelvis actually is very important because we rely on the pelvic movement for body weight shifting and more natural gait and also more energy efficient gait. So if you restricted the pelvic movement, what will happen? Actually, the gait pattern will be different, and the muscle activation pattern will also be different. So if you constrain the human pelvic movement on a sagittal plane, most likely you will end up with upper normal gait. So of course, there are a lot of devices developed for overground gait training, especially exoskeletons like this. There are a lot commercialized product out there, and a lot of rehab centers are using them right now. So let's have a look at how these devices are being used mostly for stroke patients. So you can see they still need another walking frame, and you need at least one therapist to facilitate the trunk movement, assisting the pelvic part. And of course, another therapist is trying to operate and control the movement. So if you are talking about increasing the intensity of training, they have achieved the purpose, but reducing manpower requirement, it seems like it's not possible with this approach. And if we look at another device, this exoskeleton is quite mature, but when they use it for stroke rehabilitation, they have to remove most of the parts. So only the one side is retained, and they still need a bodyweight support system, and a human is required to operate the machine. And the most important thing is that the pelvic part still need human assistance. So that means if we want to achieve the purpose of gait training, maybe this device is useful, but reducing manpower requirement is still not fully achieved. So our approach, we want to have a device that can combine the human assistance in terms of pelvic facilitation, bodyweight support, and joint movement assistance into one device, so that we can really do overground training and also reduce the requirements on human assistance. So we have a device that is going to provide the bodyweight support and provide active pelvic movement and trunk movement support, and provide functional electrical stimulation for the joint assistance. So this is the concept of the design. So this system has active wheels that is able to provide backward and forward assistance. That means we can actually provide resistance or assistance forward, and a linear actuator to provide bodyweight support. And one interesting part is that this device uses omnidirectional wheel, so that we can have the pelvic position that is assisted on the lateral movement, because we can have movement at the interface point on all three directions uncoupled. So we put a 4-stroke sensor to sense the human movement intention, and then we can achieve 3-direction active control, forward and backward, pelvic rotation, and also the upward and downward assistance. So this is a little bit more detail of the active degree of freedom and passive degree of freedom. We place IMU sensors on the 2 legs and also the trunk to sense the human gait parameters. And the 4-stroke sensor is the main user interface. So once the patient wants to move forward, the 4-stroke sensor will be able to detect. And also the pelvic part also, because it's a 6 degree of freedom 4-stroke sensor. So when the patient need to shift the body weight, or the device will be able to sense the lateral movement and provide assistance accordingly. So this is the device that we used during our clinical study. So it's this is like we don't cover everything, so it's exposed. The device is in this form with 2 omnidirectional drive, omnidirectional wheel, and 4-stroke sensor, linear actuator. So let's have a look at the IMU sensors that we place. This is IMU sensors made in our lab so that we can better integrate with the system and also the functional electrical stimulation. So the gait parameters are detected and by the IMU sensors, and IMU sensor information is going to be fit into the FES stimulation, and the FES stimulation is on the lower part of the limb, so that this is basically to prevent the foot drop. So this is how the signals are being used for the assistance for the FES. So basically, we want to close the loop and sense the angle, to use the dorsiflexion angle to control the FES amount in terms of amplitude of the current. So this is how the devices look like. We have made two devices. One is slightly smaller and better equipped, which is the aesthetics part, but functionally they are the same. So I would like to quickly go through one patient trial experiment. This project is still ongoing, so we have not conducted large-scale experiment yet. We stopped almost 2 years due to the pandemic and other patient recruitment situations. So one single stroke patient, 90 months after stroke, and right side paralytic, and we dropped through. So we conducted trials. Maybe straight away go to this. So in each session, the patient will walk along this pathway about 12 meters and walk for 2 rounds for 15 minutes each. And we provided like 7.5% of the body weight assistance force to move a little bit forward. Body weight support is about 10%, and then functional electrical stimulation to lift the dorsiflexion. So here is how the patient walk without the FES. So the first session, when the patient face cam, you can see the drop foot. You can see this device actually is like a wobbling around. Actually, it's because for the omnidirectional mobility to function, the interface point actually is fixed, but the whole frame need to be controlled in a way that is moving on the lateral and in the same time rotating, so that the device is actually providing assistance in all the directions at the pelvic point. So in the second session, once the FES is turned on, you can see that not very obvious, but still can see that the patient is walking more regularly in the pattern, and also the dorsiflexion is much improved. But if we look at the 5 sessions, after 5 sessions, so this is the first session, and this is the after 5 sessions. From the video, we can see slight change, but if we look at the gait parameters or the walking speed, the first session, actually the patient walks much slower and take a long time to make the turn. But after a few sessions, the speed is more uniform and it takes less time for the patient to turn around. And the average speed is about from moving from 0.3 meter per second to 0.4 meter per second. So speed is increased. Here is the average data. So we can see that steadily the speed is increased. And if we look at the frequency of the gait pattern, we can see that initially the pink curve is the first trial. And after, in the 5th trial, we can see a dominant frequency. That means the patient is walking at a steady frequency. And if we look at the FES stimulation after a few trials, the FES sense the angle, and also the stimulation is increased, so that the dorsiflexion is doing better in a sense. So to summarize, this device we developed as a pelvic support and omnidirectional mobility drive to facilitate the pelvic movement, body weight support, integrated with functional electrical stimulation, and the preliminary result seems quite promising. The next step, actually, what we are doing is we're trying to integrate an active exoskeleton with a knee and ankle joint, but with cable drive, so that it's still only 2 joint assistance for the knee and ankle plus this device. And we're going to do clinical trials on that in the next, maybe next year. Thank you. That's all I have. Thank you.